right. So we were looking at linear regression, right. So we are assuming that the x is coming from RP, but I told you that it is not necessarily that it has to come from the real numbers, and we talked about various ways in which you can encode the data and so on and so forth. And then right, we assume that the y comes from R, and I told you depending on the circumstances, so we will talk about the input matrix X, okay, which might be of n cross p plus 1 or n cross p, right. So it will be n cross p plus 1 when we actually have an explicit intercept, right. So a beta naught. So to account for the beta naught term, we will have a column of 1s added to the data, right. The input, instead of thinking of it as a p dimensional vector, we will think of it as a p plus 1 dimensional vector, and when I do not have the intercept, okay, it just becomes a p dimensional input, right. So that is the basic setup that we have, and we are essentially looking at minimizing sum squared error, right. So we looked at the simple linear regression, right. We looked at the case where there were like multiple inputs, and we looked at how you can interpret that in terms of single variable regression, univariate regression, right. This is essentially what we looked at in the last class, and so this class we will go on to look at a little more complex things that you can do with linear regression. So linear regression is great because it is so easy to solve, right, and it is very efficient, it runs very quickly and all that, but there are a couple of drawbacks to linear regression. So the first one is that if you remember, I was mentioning in last class also that by doing this least squares fit, you are actually getting a fit that has very low variance, but it also has how much bias? Okay, did I say that? In fact, I think people are hallucinating. So what I did say is that if you do least squares fit, and if linear happens to be the right choice, then least squares fit gives you the zero bias solution, okay, right. So least squares fit gives you zero bias solution, but the problem is the variance can be relatively high, and it turns out that by not just doing the straightforward least squares fit, by doing more tricks with the data, with the models that we have, we can trade off a little bit bias, okay. I am going to get a biased estimator for the fit for the line, okay. I am still fitting straight lines, okay. I have not done anything different, I am still fitting straight lines, but the fit I am getting will no longer be a bias free fit, but then I can reduce the variance a lot more by adding certain constraints, additional constraints to the problem, okay. So essentially what I would really like to do is reduce the number of variables, okay, which I am trying to fit. Instead of trying to fit p plus 1 variables, if I can somehow reduce the number of variables, what is this equal to? It is equivalent to setting some of the betas to 0. So if I can somehow set the betas to 0, some of the betas to 0, then essentially what it means is I have lot fewer parameters that I am estimating, right. So the fewer the parameters that I am estimating, the lower the variance still, right. But because I am now restricting the class of models that I am going to be looking at, because I have to set some numbers to 0, so my bias will go up slightly, right. This is assuming that I am fitting straight lines, straight lines are the right things to do, but still my bias will increase a little bit, right, in this case. Of course there is always this residual bias because the language of straight lines is not powerful enough, so that bias is still there, we are not talking about that, right. I am saying even assuming straight lines are the right thing to do, if I am going to force certain coefficients to be 0, I am increasing the bias in the estimator, right, but the variance will go down because I have a lot fewer parameters that I am going to estimate, okay. So that is essentially what we are going to look at, and so what I mean by subset selection here is that I am going to select a subset of the input variables to use for fitting the line, okay, right. So one thing is we can reduce the variance significantly, and therefore we can improve the prediction accuracy of the model, okay. That is one of the reasons we would like to do subset selection. Is there any other reason you can think of for wanting to work with a few smaller subset?
Less computation. Less computation.
Less computation, yeah, but it's a question of that you have to do more computation to figure out what the subset is and so on and so forth. Yeah, but less computation is one answer, but there is another one. I think I heard somebody say that. Huh? So someone or the other speaks with you synchronously always. See a trend. No, there's yet another major advantage. I mean, huh? Yeah, so related to this, right. So there are variables which could potentially have high noise, and so it will end up with a small coefficient, right. But then if I tell you, okay, here is this model and it has like 135 coefficients, right, it becomes hard for you to even figure out what this means, right. Instead of that, if I tell you, okay, here is this model, you gave me 135 variables, but these are the 4 important variables that I need for doing a linear fit, right. Now it is much easier for you to interpret what is going on, right. So interpretation is a very big component of any kind of data analytics that you want to do. Like ultimately what you are doing with machine learning is trying to understand the data, right. So one of the things you would like to have is interpretability, right. So the first one is to okay, this is interpretability and that is prediction accuracy, right. So there are many ways of doing this. The simplest kind of approach is essentially to take this literally, right, and try to select from subsets of features, right. So why is that a simplistic approach? So why is that a simplistic approach? Oh, come on, it's easy. It's combinatorial. Huh? Exactly. So just do subset best subset selection. Essentially I would say that, okay, here first pick subsets of size 1, subsets of size 2, subsets of size 3 and so on and so forth, right. And it turns out that which you can see yourself if you start playing around with some linear regression tools, that what is the variables that go into the best subset of size 1, right. Basically the one best variable need not figure in the best subset of size 2. So it does not have a nice inclusion property. So for it to have a nice inclusion property, you need to have certain very nice conditions on the data set. So in general it does not have this inclusion property, right. So you have to just redo the whole thing again. So it is not enough if you just do one, so if you say, okay, you can't be greedy basically. I can't say I will do the first subset and then I will just add the one best variable to it and then I will find the next one. So essentially you have to do a combinatorial selection. So people have come up with very clever ways of organizing this, right, and in fact of using QR decomposition to do things more rapidly. I am not going to go into details of that, but then up to like 30 or 40 variables you can scale well, right. I mean you can hope to get answers in your lifetime kind of scaling, right. But if you go for much larger variables, right, much larger number of variables, like many problems of interest like in text or image domains and things like that, then there is no hope to do an exhaustive search, right. But that is a baseline which you can do. People actually come up with algorithms which do this kind of best subset selection, okay. So there is one very interestingly named algorithm called leaps and bounds, okay, which does pretty efficient subset selection, but just a more of a informational thing for you, right. Next thing is forward stepwise selection. So any guesses what that is?
One variable at a time.
Exactly, it's being greedy, right? It's just trying to do best subset selection by being greedy. So you start off with, so what is the feature you would for sure want to have?
Higher coefficient.
All ones, okay, you need the intercept, right? Otherwise your line has to pass through the origin, okay. So you need the intercept, you start with the intercept, okay. So what should be the coefficient for the intercept? We already looked at it before. The mean of the y's, right? So that will be the coefficient. So you already have fitted that. So now what you do is you start off with that variable, okay. Now then you add the next one, okay, right? Some xi, add that as the next variable, such that it gives you the best fit modulo the set they have already taken. So you are not going to disturb all the variables you have taken till step k, okay. Now we will add a new variable such that among all the variables I could add at this k plus 1 stage, this one gives me the maximum improvement in the performance. So how will I measure performance? Some kind of residual error on the test data, right. So that is how I measure performance. I keep doing this until a point where the error does not change much. Is there any other thing I can say? So the residual is, right, so orthogonal to any of the other directions I could add, right. That is one thing which we know of, right. So we know that at the end of the right fit you get, the residual will be orthogonal to the space spanned by the x's, right. That means individually if I take any of the x's, right, the residual will be orthogonal to that individual direction as well. So when I find that none of the directions that are left have any kind of component along the direction of the residual, then I can stop, okay. Or I mean that might take a long time to do, because that might happen only when I have the full least squares fit. So I can stop when the residual drops below a certain threshold, right. You can say, okay, I am happy with the prediction accuracy you are getting, I will stop here, okay. So there are many ways of doing that, right. So the other way is to do what will you do in this case? I will start with the fit that has all the variables, okay, and then I will keep dropping one by one, right. So one thing to note is that you can do this if the number of data points is greater than the number of dimensions. So then you can actually find the fit. If p is greater than n, then as people pointed out last time, the formula itself that we are using is no longer valid, right. So because its matrix will not be invertible, so we will have to think of other tricks for doing the fit and so on and so forth. But forward stepwise selection you can do even if p is greater than n, because I am anyway fitting one direction at a time, right. So it's that is fine, right. I am adding one direction at a time, I can keep going until I reach n directions, at which point I should have a full least squares fit, okay. Yeah. So and people actually, I mean, come up with all kinds of variants on this. So one thing which you could do is think of some kind of hybrid approach, where I keep adding and deleting directions, right. So if you remember, we talked about how greedy is not always the best way to grow things, right. So you can grow up to a certain level, okay, and maybe then dropping one of the earlier dimensions will actually give you a slightly better performance, could be, right. So that is one possibility, and right. So you could do some kind of a hybrid version of this. So one thing I should point out here, so you might think that forward stepwise selection, because it is greedy, is going to be much worse than best subset selection, right. So it turns out that in many real cases, many real data sets that you work with, right, the greedy selection is actually not a bad thing to do, right. In fact, so many statistics packages like R will allow you to do this, right. So you would not find this in many of the machine learning tools like Weka, right. So they would not have this kind of a forward feature selection, things like that. They have other ways of doing feature selection which we will talk about later, right. But then statistical packages actually have this stage wise addition of features because they seem to work well on a variety of data sets, okay.